When a massive power substation violently trips offline, the event happens so quickly that standard grid monitoring barely registers the cause. For decades, grid planners have relied on positive sequence phasor domain models, often called RMS, but hyperscale AI data centers possess electrical characteristics that these traditional planning tools were never designed to capture. RMS models assume a quasi-steady-state sinusoidal balance. They evaluate the grid in 10-millisecond increments, which averages away the high-speed sub-cycle dynamics where modern power electronics operate. To address this mathematical blind spot, grid operators now require developers to submit electromagnetic transient, or EMT, studies before approving a multi-hundred megawatt interconnection. EMT modeling replaces smooth averages with raw physics. It solves nonlinear differential equations directly in the time domain, calculating instantaneous point-by-point waveforms. This is a chart comparing the resolution of both models. On the left, we see a stable RMS sine wave calculated at a 10-millisecond step. The right side shows the exact same event modeled with an EMT waveform at a 10-microsecond step, revealing chaotic high-frequency distortions. That jagged distortion peak represents a real physical event. These microsecond-level transients exceed safe operating thresholds and can cause converter equipment to trip, an event that is completely invisible on the left RMS wave. While the need for an EMT study is clear, the actual engineering challenge is mathematically constructing a viable model of a hyperscale facility without causing the simulation software to crash. Integrating converter-dominated AI data centers using traditional average models prevents planners from identifying the high-speed triggers that lead to localized grid collapse. The requirement for an EMT study typically triggers when the short-circuit ratio falls below 2. This indicates a weak grid condition, where the available fault current is low relative to the massive power electronic load. Engineers use EMT to hunt specific failure mechanisms, starting with oscillatory interaction caused by the aggressive power ramps of AI training cycles. When a data center load fluctuates rapidly, it can excite the natural oscillatory modes of the grid, creating severe torsional stresses in the physical shafts of nearby steam and gas turbine generators. This diagram shows the physical impact of those oscillations. If the power demand fluctuates between 10 and 50 Hz, it hits the subsynchronous torsional frequency range, physically wearing down the rotating hardware of the generator. The second diagnostic requirement is validating sub-cycle fault ride-through capabilities. The model must capture how the facility's front-end converters and uninterruptible power supply systems respond to severe voltage sags in the span of microseconds. The third requirement is power quality analysis, specifically targeting rapid switching transients, breaker restrikes, and voltage flicker. In weak grid conditions, the control loops of hundreds of individual converters can interact, resulting in hunting behavior that degrades local power quality and propagates through the transmission network. EMT simulation is the only diagnostic tool that reveals these high-speed control interactions before they destroy physical infrastructure. To run these simulations, engineers need accurate data. Standard library models used in rapid RMS studies lack the fidelity required for EMT work. The primary bottleneck in the interconnection process is acquiring exact device-specific logic directly from original equipment manufacturers. Planners must obtain precise hardware parameters, including the facility's exact load composition ratios and the maximum active power ramp rates. This schematic represents the level of detail required. Engineers must map the exact protection settings, such as AC and DC undervoltage trip thresholds, to build an accurate simulation. This includes programming precise momentary cessation walk-in times to model how the facility recovers and ramps power back up after a fault clears. Engineers also require unencrypted AC network impedance data to accurately map how the data center's internal electrical system couples with the bulk grid. An EMT model is only as reliable as the proprietary hardware logic fed into it. Relying on generic assumptions leads to simulated safety but real-world instability. Once the data is collected, modelers face a strict computational limit, the resolution to computation trade-off. The highest fidelity representation is the switching model, which calculates electrical behavior at microsecond intervals. Applying a switching model across thousands of converters in a 200-megawatt facility causes a computational collapse. The processing power required is too high. To make bulk grid studies feasible, the industry uses the average value model. This is a comparison of the computational payload. The dense 100 kHz pulses of the switching model on the left cause the simulation to grind to a halt. On the right, the smoothed average value curve allows the clock to run efficiently at a 50 microsecond time step. Despite losing individual switching events, the smoothed line perfectly tracks the broader control dynamics and grid responses necessary for interconnection screening. This involves a mathematical trade-off. Average value models imperfectly approximate DC link losses, which slightly alters the transient response, but they remain the most practical tool for wide area studies. Switching models are reserved strictly for highly localized tasks, such as harmonic compliance testing, where the hardware topology directly dictates the result. Building an EMT model is an exercise in strategic abstraction. Engineers must decide which high-frequency noise to blur in order to process the larger stability picture. The rise of parallelized AI training alters how data centers draw power. Instead of a flat, steady consumption, the demand occurs in massive, correlated batch cycles. If these power cycles fall into the electromechanical frequency range of 0.1 to 2 Hz, they can interact with the natural oscillatory modes of the grid and cause sustained, forced oscillations. This creates a newly identified grid risk, known as distributed commercial and industrial load reduction. This map shows shared AI training connecting separated data centers. If a lightning fault strikes one node, power across all 3 facilities instantly drops to 0. The synchronized loss of hundreds of megawatts shocks the grid, triggering frequency deviation warnings. Because the AI workload is parallelized, an interruption at one facility forces all participating facilities to immediately halt their processes and drop their load in unison, even if those other sites experienced no electrical disturbance. Distributed training turns separate facilities into a singular superload, allowing a localized fault to destabilize the grid from hundreds of miles away. To manage this complexity, engineers use a modeling in layers philosophy. This approach represents only the specific control loops and grid-facing converters that shape the disturbance, while abstracting the internal facility components that do not impact the grid. Beyond modeling, data center developers must implement localized hardware mitigations to dampen these intense power fluctuations. This image shows a rack-level battery energy storage system. These units provide a perfectly smoothed power output, absorbing fluctuations before they can reach the grid. These fast-acting grid-forming batteries, combined with GPU software power smoothing, act as a buffer to dampen oscillations before the point of interconnection. EMT simulation provides the mathematical lens required to engineer these defenses and maintain the integrity of an AI-powered grid.